Previously, we've been able to compare series to integrals in order to determine whether they converge or diverge. Now we're going to look at a way to compare two series in order to be able to determine whether one of them is converging or diverging. To motivate this discussion, we're once again going to contemplate thinking of series as areas on a graph. So if we look at this graph, we note that we have some sequence b sub n, we're going to identify each of these corner points on a rectangle. That's going to be the point n comma b sub n. So we have 1, b sub 1, 2, b sub 2, and so on and so forth. That means that because each of those rectangles has a width of 1, the area of that rectangle is exactly equal to b sub 1. The area of the next rectangle is b sub 2, and so on and so forth. So what we see is that we can represent the blue area on here as the sum from n equals 1 to infinity of the sequence b sub n, which is how we represent our series. Similarly, let's look at the orange rectangles, and again we're going to take each corner point to represent a value in our sequence. So this is the point 1, a sub 1, 2, a sub 2, and so on and so forth, which makes this orange rectangle here have an area of a1. The next one has an area of a2, and so on and so forth. That means that we can represent the orange area as the sum from n equals 1 to infinity of a sub n. Now we notice that for all of our values here, our a sub n was less than or equal to b sub n. That generates an inequality for the areas. Then we can see that the orange area is smaller than or equal to the blue area. This is going to form the basis for our comparison test. So the comparison test for the convergence of series tells us that if we have two sequences, a sub n and b sub n, so that a sub n is less than or equal to b sub n, and both are positive, it then follows that the sum from n equals 1 to infinity of a sub n is less than or equal to the sum from n equals 1 to infinity of b sub n. Because of that, we can conclude that if the sum of the a sub n's diverges, if the smaller series diverges, then the larger series b sub n must also diverge. Similarly, we can conclude that if the larger series b sub n converges, then the smaller series must also converge. Let's explore how this works by examining the sequence, the sum from n equals 1 to infinity of 1 over n squared plus 5. We know that if we add 5 to a number, it gets larger, which means that 1 over n squared plus 5 must be smaller than 1 over n squared for n greater than or equal to 1. That then tells us that the sum from n equals 1 to infinity of 1 over n squared plus 5 must be less than or equal to the sum from n equals 1 to infinity of 1 over n squared. We can apply the p-series test for convergence to the series 1 over n squared. And we can see with a p-value of 2 that series converges. That then means that our series 1 over n squared plus 5 also converges because it is smaller than a convergent series. We can use similar techniques to look at the sum from n equals 2 to infinity of 1 over n minus 1. Notice that subtracting 1 from n makes it smaller, which means that 1 over n minus 1 is greater than or equal to 1 over n. This tells us that the sum from n equals 1 to infinity, or rather n equals 2 to infinity, of 1 over n, the smaller sequence must be less than or equal to the sum from n equals 2 to infinity of 1 over n minus 1. But our p-series test tells us that this sequence, or this series on the left, diverges because we have an n value of, a p-value of 1. So this is divergent, which must mean then that the series in question also diverges because it is larger than a divergent series. All right, a final summary of what we know. If we have two series and the terms of one of those series are less than or equal to the corresponding terms in the other series, then that means the series itself must be smaller, so that if the smaller series diverges, the larger one must also diverge. If the larger series converges, then the smaller series must converge as well.